Hi, this is a makeup video for CS596 machine learning, and the topic for this lecture is principal component analysis. Okay, so in this lecture, we will talk about the definition of PCA and why we need to use that technique. And then we will jump into the details of how to conduct PCA on paper, and I will have some Python code as an example. Okay, and then finally we will reach some interesting applications and commonly used applications for PCA. So basically speaking, PCA is a dimensionality reduction technique. So it can help remove the redundancy or redundant dimensions in your data, and as a result, the most important dimensions are kept or reserved in your data sets. Okay, so it is a technique that usually applies to high dimension data. So in this course, in this machine learning course, so far we have encountered a lot of high dimensional data. For example, in the topic that we have just covered in the previous week, we introduced the word embedding data, and a word embedding is usually of very high, well, not very high, but it's of 100 to 300 or even higher dimensions. And for image data that we have used so far in this course, we used 16 by 16 images, 64 by 64 grayscale images, and if we flatten all the pixels in those data sets, and they are of pretty large dimensions. And another type of data that we haven't used in this course is genes data or bioinformatics data. So, for example, how to interpret the meanings of genes which may have multiple dimensions is difficult, because higher dimension data is always hard to interpret clearly. So basically speaking, PCA is a technique that helps to reduce the dimensions in data and to keep those that are critical, and so that's the interpretation of the data and visualization is much easier. Okay, so now let me give an example of high dimension data sets. So if you look at this data sets of birds that describe the weights, the wingspan, the length of several different kinds of birds. So given these data sets, you may wonder that how you can visualize the data, okay? Because you have more than two dimensions, right? So if it's a 2D data set, you can easily plot all the data points on the with axis and the y-axis. But when it has more than two features, to visualize the data sets is not an easy task. Okay, so you got to select the right features or the right dimensions that you want to visualize, so that the plot is informative, or so that the plot is telling you some salient patterns. Okay, and not all the features are capable of showing the most significant patterns in the data sets. Okay, so another question is the collinearity, or how those features are correlated. So, for example, in this example, the wingspan and weight and length of a bird, they are all kind of related, because larger birds tend to have larger weights, larger wingspans, and so on, right? So it is important to find what are the most significant features to the data sets. Okay. And another example is the students' datasets. We have weight, heights, like SAT scores, IQ to describe the student's profile, for example, in this university, in college. And we can ask the same questions, like how do we visualize the dataset? Like, of course, we have different purposes for different visualization techniques. And how do we choose the features correctly in order to fit different purpose to meet different purposes is a quite tricky task. Okay, and of course, how to measure, how do we consider the correlation between the features is also important here. Okay. So now we propose like two standards of what good dimensions a good dimension should be. Okay, so because we have given a high dimension data set, we want to keep those important dimensions, but remove those trivial dimensions in order to have a better visualization or description of the data set. So we need to define what we mean by good. Okay, so we have two standards here. The first one is a good dimension should have a higher resolution. That means if we project all of our data points along this dimension, then the data points should spread out instead of clustered together. Because only when the data points are spreading out along that dimension, we can tell the differences. We can distinguish different data points apart. Otherwise, they are all in one cluster, and then there's no difference between those data points. Okay, so we want dimensions that along which data points spread out. And the second standard is that those selected good dimensions should be independent from each other. So that is another saying of we don't want to have highly correlated dimensions. Okay, because if two dimensions are extremely correlated, then this is just redundant features. We don't want to use two features to describe one data if one feature is enough. Okay, so here are the two basic standards or consideration for choosing dimensions on high dimension data sets. So what PCA does is to find a set of dimensions such that all those dimensions are, I use the term orthogonal. So it means all the dimensions selected are independent. And also, those new set of dimensions are ranked according to the variance of data along them. Okay, so this variance of data is just a degree of how data points spread out along those dimensions. And those dimensions are ranked in such a way that the most informative dimensions are ranked at a higher position. Okay, so this is basically the function or what BCA tends to achieve. Let's get to know PCA from a very simple example here. So let's take part of the birds dataset, and we just include the two features, the weight and the wingspan. And suppose that our goal is to reduce the dataset from a 2D space to 1D space. Okay, so though this is not a common practice in processing data, because 2D data set is already convenient to plot, but we're just using this extreme example to show how PCA works. Okay, so now given these raw data sets, of course we can plot it immediately on the 2D space. So we can see that the blue dots here indicates the positions of those data points, those 6 birds data points in the 2D space. Okay, and before we carry out the next step, we can compute some helper values for each feature. So the mu1 here is the mean values of the weight feature. Okay, and sigma 1 is the standard deviation of the weights, and mu2 is the mean values of wingspan, and sigma 2 is the standard deviations of wingspan. Next, using the mu's and sigmas, we just computed at the previous step. We can now normalize all the data points. Okay, so how we normalize the data points is to minus the mean values from that data points and then divided by the standard deviation, so that each feature is normalized into a normalized scope. Okay, so now we call the normalized features x1 tilde and x2 tilde. Okay, with this little curly as a hat for if above x. Okay, so now if we plot these normalized data sets, you can see that basically the shape of the data points doesn't change as compared to the previous plots. Okay, in the previous plot, the data looks like this way. Okay, it looks like this way, and after we normalize data sets, we just kind of move all the 6 data points into the position where they are centered around 0 point here. Okay, so the shape doesn't change. We just move and scale the data points. Okay, so now next we need to consider the goal. So remember, the PCA's goal is to find the dimension that best describe the data. Okay, because now we are reducing from 2D to 1D. Okay, so there will be only one dimension left. So therefore, our only consideration is that we just need to find one dimension that characterizes as much variance as possible. Okay, in another word, we want the data points to spread along that new dimension as much as possible. Okay, remember, our second consideration is that all the remaining dimensions should be independent of each other. But right now, because we only have one dimension left, so there's no such issue as independency here. Okay, so now we just consider how to select a dimension that's the data, all these 6 normalized data points spread as much as possible. Okay, so the problem in our goal becomes to find a good dimension to project all of our 6 data points. Okay, so for example, we can choose this candidate dimension. Okay, if the dashed line is the dimension that we want to choose, then we want to know that how much total variance that this dimension can account for, or we want to measure or want to calculate the total variance along this dimension. So mathematically, how we measure this total variance is that we first project our data points onto that dimension. Okay, given this dashed line as a candidate dimension, for example, we can project our first point P1 onto that dimension. Okay, and then we can measure the distance of the projection from 0 points, okay, by measuring the length from where the projection is to the 0 points. Okay, so this D1 is the distance for the projection for the data, for that one data point P1. Okay, and we can do this for all the data points, for all the normalized data points. For P2, we will have D2, and P3 we will have D3, and so on. Okay, so we do this projection for all the data points. And after this step is done, we can sum up the squares of the projections of the distances. Okay, so this distance, this summation of D1 square to D6 square is the total sum of squares of the projections. And this total sum of squares can be used to measure the total variance of all the data points along this candidate dimension. Okay, so if that total sum of squares is large, then we say the total variance explained by this candidate dimension is much. In another word, what we want to do is to maximize this total sum of squares, because we want to find a candidate dimension that has as much as total variance as possible. Therefore, we want to find a candidate dimension that maximizes this quantity. Okay. So in theory, we will have infinite number of choices in terms of which candidate dimension to project those normalized data points, right? So we can choose the one that we have chosen before, or we can rotate this dimension a little bit by using alternative one like this, or we can further rotate it. Okay, so anyway, the goal is to choose a dimension that maximizes the total sum of squares. Okay, so imagine or assume that we have find a dimension in this direction, and along this dimension we make sure that the total sum of squares is maximized. Okay, so assume this is the direction, and then we call this dimension the first principal component, or PC1. Okay, and PC1 has such a quantity, has such a property that we project all of our data points onto PC1, then the sum of squares is maximized. Okay, and then we can use a unit vector, which means a vector of length 1 to denote or to indicate this PC1. Okay, in our case, the unit vector is 0.94 and 0.34. Okay, and we assume that this is the so this is the unit vector that indicates the direction of this PC1. Okay, and remember that this new dimension U1 is a linear combination of x1 tilde and x2 tilde. Okay, so we are representing this new dimension within the Cartesian system, or the coordinates of x1 tilde and x2 tilde. We are representing U1 with x1 tilde and x2 tilde. Okay, so actually U1 can be written in this way. It's 0.94 times x1 tilde plus 0.34 times x2 tilde. Okay. So given the first principle 1, PC1, we can easily find the second principal component, PC2. Okay, so now recall the principle of PCAs. We want to find the dimensions so that they are independent of each other, or they are orthogonal. So as long as we have PC1, then we just need to find the direction that's perpendicular to PC1. Okay, so as indicated by the green dashed line here. Okay, and here on this slide, there's a typo here. So the wingspan should be wingspan normalized. Remember, we are all in a normalized space. Okay, so anyway, this green dashed line is the second principal components. And if you if you project all the data points to PC2 and compute the total sum of squares, you will find that this total sum of squares along PC2 is much smaller than PC1. Okay, and also we can use a unit vector to represent PC2. Okay, so U2 is negative 0.43 and 0.94. Okay, so these PC1 and PC2 are orthogonal towards each other, which means the U1 and the U2, they are perpendicular to each other. Okay, so we can write this into a dot product. So the dot product or inner product between the two vectors, U1 and U2, are 0. Okay, and we should notice that because PC1 is the first dimension that we choose, therefore the total variance or the total sum of squares of along PC1 is much bigger than PC2. So given PC1 and PC2 found, what we can do to the data, to the normalized data set data points is to rotate our 6 data points onto the new basis, or onto U1 and U2. Okay, now we are using PC1 as our x-axis and PC2 as our new y-axis. Okay, instead of using the original x1 tilde and x2 tilde, because if we represent the data using these principal components, we have better, so the data have better resolution along PC1, because the total variance is along PC1 is maximized. Okay, so compared with the original data points, in which all the data points are not rotated, okay, we can find that it's kind of easier to explain the variance among the data points. Okay, because PC1 is maximized, and along PC1 the total sum of squares is maximized. Then PC1 is explain more patterns or explain more information in the data points than the original feature x1 tilde and x2 tilde. Okay, PC1 explains more variance than weight, or weight normalized to be strict. Okay, so now let's look at the details of how to compute those principal components like PC1, PC2, and so on. Okay, so we can denote the principal components as a unit length vector U. Okay, remember in the previous slide we have U1 for the PC1 and U2 for PC2. So because we are still using these two-dimension data sets as data as example, so the principal components vector U has two elements, U1, U subscript 1, U subscript 2. So these are the two elements of a two-dimensional vector. Okay, so now we need to project all the data points onto this principal component. Okay, for example, for this data point x tilde I, which is the i's data point in our data sets, which also has two elements, x tilde 1, x tilde 2, and we can then project this this vector x onto the principal component u. Okay, so how do we compute the length of the projection? And this length of the projection of x along u is just the inner product, okay, by u transpose times xi. Okay, and if we write it clearly into by extracting all the terms here, it's u1 times x1i plus u2 times x2. Okay, so this quantity is the inner product, which is also the length of projection of xi onto u. Okay, remember our goal is to maximize the total sum of squares for all the data points. Therefore, we can simply define SS as the summation of all the inner products. Okay, SS is just the summation of all the of data points of inner products of all the data points. Okay, so if we extract the terms within this sigma operation, it becomes like this. Okay, and we'll see later that this term on the right can be further simplified using matrix notations. Okay, now we represent the normalized data into a matrix, okay, which has two rows, which corresponds to the two features, and m columns, supposing that we have m data points. Okay, and then the sum of squares written in this form is equivalent to this matrix denotation, matrix form. So you can write the transpose of the unit vector u to the left, and the vector u to the right, and what's in middle is x tilde times x tilde transform. Okay, so this matrix multiplication is in the middle. So this is how we define, and if you replace x tilde with this complete form, you place this complete form into this formula, you will find out that it is indeed the case. This form is equivalent to this form. Okay, therefore the problem becomes maximizing this quantity SS, and we add a term 1 over m just for convenience. Okay, so we are maximizing u transpose times 1 over m times x tilde transpose and times u. So this is the quantity that we want to maximize, and of course under the constraints. Okay, because we set the constraint that the principal component should be a unit length vector. Therefore, the norm of u should be 1. Okay, so hopefully this reminds you of something similar that we have come across before when we talk about constraint optimization problem. So this looks like a typical constraint optimization problem. We are maximizing some quantity under some constraints. Okay. Okay, so now let's try to solve this typical constraint optimization problem. Okay, so let's look at the form again. The total sum of squares in this form, 1 over m times SS, is the quantity that we want to maximize, but we have this constraint in the equation form, and the constraint is that the norm of the vector u should be 1. Okay, so if we rewrite the matrix x tilde with the original feature, with the original data. Remember, the original data is not x. Okay, so it's not x tilde but x. How we get x tilde is by first minusing the mean values for each feature. Okay, so x1 is minus from the mean values of the first feature, and divided by the standard deviation of the first feature. Okay, so this is how. So on the left part here is how the x tilde looks like. Okay, if we use the original data x and mu to represent it. Okay, and x tilde transform looks like this. So if we further rewrite this to matrix multiplication onto the right form, it'll be like this. Okay, so these parts in the red box is the variance of xi. So this is the result of taking the first column here and carry out a dot product or inner product with the first row. Okay, which results in exactly this form, which is the total variance of xi. And similarly, the bottom right column, the bottom right elements is the variance of x2 or feature 2. Okay, and what's here, the top right and bottom left, they are the covariance between xi and xi. Okay, it's the summation of the difference between x1 and its feature and its mean value times x2, the difference between x2 and its mean value, divided by the standard deviation of x1 of feature 1 and feature 2. So this is the definition of the covariance between two variables, between two random variables, x1 and x2. Okay. So in terms of the meaning of those covariance, they represent how much xi and x2 are related, how the two features are correlated or move in the same direction. Okay, so if you look at the shape of x tilde times x tilde transpose, it's actually a pretty small matrix. It's just a 2 by 2 covariance matrix. Sometimes we can write it as big sigma. Okay, and now let's look at the problem. We want to solve this maximization problem, and how we solve it is to use the Lagrangian multiplier. Okay, because the constraint is in the simple form. The constraint is in the equation form. We can create a Lagrangian term and modify our optimization goal into this one. We convert the constraint problem into a non-constraint problem as this. So the new optimization goal is to maximize u transpose times what's in middle is the covariance matrix times u minus lambda. Okay, so this is how we construct a Lagrangian term. Okay, and this is the original constraint form. So the dot product minus 1. Okay, and now this is our Lagrangian, and what we need to do is to find the value of u that maximizes this Lagrangian. Therefore, we just need to take the derivative of this Lagrangian with respect to u, which results in this form. Okay, the covariance matrix times u minus lambda times u equals 0. Okay, and this form, this equation on the right, can be further rewritten into this way. And this form is commonly used form, commonly appeared form in linear algebra. So the solution to the original constraint optimization problem is the eigenvectors of this covariance matrix. Okay, any vector that satisfies this form, any vector u satisfies this form, that's the covariance matrix times u equals lambda times u, then this vector u is the eigenvector of the covariance matrix. So this is the definition of eigenvector. Okay, so and the corresponding sum of square is just the eigenvalue which is lambda, corresponding to the eigenvector. Okay. So speaking of eigenvectors, we need to it might be helpful to look at some review of the linear algebra content. Okay, so the word eigen is a Dutch word that means self or mine. So you can think of eigenvector as a meaning of my vectors. Okay, so why do we call it an eigenvector? So you can think of a square matrix A and a column vector V. So if it satisfies that A times V equals lambda times V, okay, that means that's the definition of eigenvector. Then V is the eigenvector or characteristic vector of A, or my vector of A, and the lambda is the eigenvalue. Okay, so this equation means that because A is kind of a transformation of V, okay, a matrix A represents a linear transformation. So typically speaking, almost all vectors will change its direction when they are transformed by A. Okay, so typically speaking, if you times a matrix A by a vector V, and the results should change direction. But eigenvector is a special case that these vector V are in the same direction after you time A with V. These are the eigenvectors of matrix A. Okay, when you times A with V, the result is just a change of the magnitude of V. It just scales up the vector V by lambda, but you do not change the direction of V. So that's the specialty of eigenvectors. So such a vector is called the eigenvector of A because it doesn't change the direction once you applied the linear transformation of A upon such a vector. Okay. So let's look at some other review of the linear algebra. And this is a special spectral theorem about the eigenvectors, and it states that so if A is a square matrix, is a symmetric matrix, which means the transpose of A equals A, then we say that A is orthogonally diagonalizable and has only real eigenvalues. So this is the property of having only real eigenvalues is important here. Okay, so that means, so this theorem means that there exists real number eigenvalues and orthogonal non-zero real vectors, non-zero real eigenvectors, such that they satisfy this form. So there are n such eigenvalues and eigenvectors satisfy that A times Vi equals lambda I times Vi. Okay, and the condition is that A is symmetric. Okay, so now let's further look at a non-symmetric matrix A. So if A is an m by n, so now this time the number of rows doesn't equal the number of columns, then we can construct or can create some symmetric matrix by times A and A transpose. Okay, So if we times A and A transpose, then the result is a m by m matrix. Or if we times A transpose times A, the result is a n by n matrix, and both matrices are symmetric. Okay, and according to the spectral theorem, the two symmetric matrices, A times A transpose and A transpose times A, they should have the same non-zero eigenvalues. Okay, we can easily prove this. So let V be a non-zero eigenvector of A transpose times A with eigenvalue lambda. Then, according to the definition of eigenvectors and eigenvalues, then we should have this form, right? We should have this A times this matrix times V equals lambda times V. Okay, but now if we multiply both sides with A to the left, it becomes this, and the right term becomes like this. Okay, and we can combine the A with A transpose into this form, and it becomes like this. Therefore, lambda is also the eigenvalue for A times A transpose, and the eigenvector is A times V. Okay. Therefore, A times A transpose and A transpose times A, they have the same non-zero eigenvalues. Okay. So it looks trivial, but this is a quite useful property of when we are dealing with large matrices. Okay, when sometimes the most commonly used property is that commonly used case is that when m and n they are very different. Say in our data sets, say if A is a data set, then we have two rows, which means we have two features. But we have 500 columns, which means we have a lot more data points. Then the quick way to find the eigenvalues, so if we want to find eigenvalues of A transpose times A, which is a 500 times 500 matrix, is to find the two eigenvalues of a 2 by 2 matrix, A times A transpose. Okay, you see the trick here. Instead of finding instead of trying to find the eigenvalues of a very large matrix, we can find the two eigenvalues of the smaller matrix, because the spectrum theorem tells us that these two matrices, they share the same non-zero eigenvalues. Okay, and it turns out that A times A transpose times A, which is a large matrix, in theory it should have 500 eigenvalues, but only two of them are non-zero, and all the rest, 498, are zeros. Okay, so this property gives us a much faster way of finding eigenvalues and eigenvectors for matrices that are whose number of columns and number of rows differ a lot. Okay, so now let's look at the eigenvalues and eigenvectors of a covariance matrix. Okay, and when the original data is a 2 by m matrix, which means our covariance matrix is a 2 by 2 symmetric matrix. So there are two eigenvectors and corresponding to eigenvalues, and they satisfy these equations: sigma times u1 equals lambda 1 times u1. Okay, so what are the meanings of the eigenvalues? So the summation, so first of all, let's assume that we rank all the eigenvalues in a descending order. So make sure that lambda 1 is greater than lambda 2. So the total variance in data is a summation of the lambda values. Because previously we have seen that by maximizing the sum of squares, we are obtaining the we can obtain the eigenvectors as the solution to our optimization problem, and the corresponding eigenvalue is that value of the maximized total variance. So the total variance in data is a summation of lambda 1 and lambda 2. And the lambda 1 correspond to the sum of squares of the projections along the first principal component, which is u1. And lambda 2 is a total sum of squares along the second principal component. Okay? And therefore, we can use the ratio of lambda 1 over t to measure how much variance that the first principal component u1 accounts for. Okay? And lambda 2 over t is the ratio of variance that the PC2 accounts for. Okay? So this is a case for 2 by n data. So now let's go into a higher dimensional data set. Okay, so far the example we have are using a 2-dimensional data set, 2 by n matrix. So what if now we have an n by n, which means that each data point is an n-dimensional vector. Okay, so we have n features. So we can still create a covariance matrix in this way. Okay, by first normalize the data into x tilde and then use x tilde times x transpose, which results in a n by n matrix. Okay, so we can get n eigenvalues and eigenvectors. They all satisfy these equations. And now, similarly, we can rank all the eigenvalues in descending order. Okay, so that lambda 1 is the biggest. And in this case, the total variance in data is a summation of all the n lambda, all the n eigenvalues. Therefore, the first principal component, PC1, accounts for lambda 1 over t of the total variance. And similarly for second principal component, and so on. Okay? So lambda, all the eigenvalues, is kind of an indicator, or it measures the importance of the eigenvectors or the principal components. So the most important eigenvalue and the most important principal component is the eigenvector that has the largest eigenvalues. So now it comes to the question of how exactly we can find the eigenvalues and eigenvectors. So thanks to the package NumPy and the linear algebra module in NumPy, we can conduct this computation really fast in a really convenient way. So all you need to do is to construct your data. Like in this case, we have a 2-dimensional data x. We have 6 data points in this example. And now we just can construct the covariance matrix in this way, called NumPy dots on x and x transpose, and we call the eigenvector, function on top of this covariance matrix, and it will returns the eigenvalues and the vectors. So we can see that the eigenvalue of the first for PC1 is 386, and the second eigenvalue is 7.4, which means that the first principal component accounts for the majority of the variance in data. So compared to PC2, this one, PC1, it accounts for more than 95% of the total variance. Okay, so now we can, after we obtain the n principal components or eigenvectors out of a data that has n features, that has n original features. Okay, we can use the eigenvectors to conduct what we originally want to do. So we want to use those principal components to reduce the dimensions of data sets. Okay, so the original dimension of our data set is n. We have n features. Okay, so now we can pick the most informative or most important k principal components and use that k principal components to represent our original data set. Okay, so in this example, we suppose that data is n by n, and the covariance matrix is n by n. Now, suppose that we have computed the n eigenvectors and eigenvalues here. So what we can do is to select the top k eigenvectors with top k eigenvalues. Because we rank eigenvalues in a descending order, we can select the top k. Okay, and now we can stack the eigenvectors, the column vectors, the k eigenvectors into a matrix U. Okay, now this matrix has n rows and the k columns. Okay, that means we can span our data to a k-dimensional subspace. So this is the subspace that we create. Okay, and then we project our data points x tilde into this subspace by conducting a dot product. Okay, we can product xi tilde onto this subspace U transpose, which gives us the coordinates of xi, the original normalized data points, into this subspace, which only have k dimensions, right? Because we select k basis vectors. And the projection of the n-dimensional data sets into this k-dimensional subspace is a k-dimensional vector. Okay, so this is the dimension reduced representation for xi. So we call it yi. Okay, so we reduce the data from an n-dimensional space to a k-dimensional space. Okay. And we can project all of our examples into a new subspace. Okay, we can just times ut with x tilde, which results in a k by n matrix, which is a reduce, which means we now reduce the n-dimensional data to k-dimensional. Oh, excuse me, the picture blocks. Okay, so I'll repeat this part. Let me repeat this part. So if I project one data point, xi, and xi is of n dimension. If I times xi with the U transpose, we are projecting the x tilde I into a k-dimensional subspace, which results a k-dimensional vector, which is the coordinates of that data point xer in the k-dimensional subspace. Okay, so if we times we can do this dimension reduction to all of our database to our data points, then we will have a reduced dimension of the whole data sets. So we reduce the dimension from n to k. Okay, and y are the coordinates of data in a new subspace. So in the most extreme case, we can choose k equals 2 or k equals 3. Okay, so now it comes the practical need of visualizing data sets. So for high dimensional data, if we have more than 3 dimensions, it's impossible to visualize the 4 dimensions on the 2D space. So all we need to do is to project the original data points into a 2-dimensional subspace using the first two principal components. So which means we select k equals 2, and then we will have a 2-dimensional projection for each data point in our original data sets. Okay. So now if we look at the transformed data, okay, so if we look at the transformed y's, okay, so it has some interesting properties. If you look at the covariance matrix of the y, okay, so y is of dimension k. Remember, we reduced the original x of dimension n into a k dimension y. So if you look at the covariance matrix y, so how we get y is to use u transpose times x tilde. Okay, so if we look at the covariance of y, it becomes this. It becomes u transpose times the covariance matrix of x times u. Okay, which is just the first k lambda values as diagonal elements, and the rest of the elements are 0. Okay, because that's the property of the eigenvectors and eigenvalues. Remember, they are composed of the k eigenvectors of x of the covariance matrix in the middle here. Okay, so the result is the k diagonal matrix, and the rest of them are 0. So this means that the covariance between the k dimensions are 0. Okay, so in other words, all covariance elements in this matrix are 0. So all the k dimensions in the transformed data, they are independent of each other. Okay, so if we plot, if we have a data that looks like this, okay, then that means the covariance between the 2 dimensions are very low. And what if the covariance is large? Then the data, if we plot it, it will be like this. So in the case of the transformed data, the covariance is low, and that means the variance along those dimensions are maximized. Okay. I'm blocking myself again. So if you look at the left, the covariance between the 2 dimensions is very low, and the data will look like this. And if the covariance is big, then the 2 dimensions, the plot will look like this, which means this is on the right. This is not probably the best way to visualize the data, because we are not choosing the 2 dimensions that are independent of each other. And in this case, on the left, the 2 dimensions we choose are more independent of each other, because the covariance is very small. Okay, so this 0, in one word, this 0 in the covariance matrix means that all dimensions are independent. Okay, so other than the current method of computing the principal components, of conducting a principal component analysis, we have another method, which is to use the singular value decomposition, SVD. Okay, so the thought behind is that we directly decompose the data x into 3 components, which results in three parts on the right. So U is a n by n unitary matrix. By unitary, we mean that the norm for each row or each column is 1. And in the middle is a n by n rectangle diagonal matrix. Okay, and the diagonal elements correspond to the singular values. And on the right, the V transpose is an n by n unitary matrix. Okay, so if we use this X to replace the X in the covariance matrix, okay, so we replace this U times sigma times V transpose into this form, we'll have because V and U, the V is a unitary matrix, so the results of V transpose times V is gone, is all 1. Therefore, this term becomes this term. Okay, and what's in middle is the eigenvalues. Okay, so eigenvalues is essentially the square of singular values. Okay, and the U's, they correspond to the principal vectors or principal directions. Okay, so therefore, in theory, this singular SVD method is faster than finding the eigenvalues or eigenvectors. So now let's summarize the contents covered so far. So given the data sets, in order to perform PCA on the data, we will first need to normalize the data sets, okay, into X tilde, which is n by n dimensions. So, and we need to find the eigenvectors and the eigenvalues of the covariance matrix, which is in the form of 1 over n times X tilde transpose. And suppose that we have find all the n eigenvectors and all the n eigenvalues. And then we should observe whether a small number of eigenvalues are much bigger than all the others. And this is usually true for most of the cases. So we can choose the first k elements, right? And then we can reduce the dimension from the n to k. Okay? And then we can try to interpret the principal components, like which ones are the most important, which ones are the most informative. Okay. So if we look at a concrete example of the birds datasets again, so we can use PCA to try to have a better interpretation of the features. Okay, suppose that we have 3 original features with length, wingspan, and weight. And our X is a 3 by 100 dimension data sets, so we can get a 3 by 3 covariance matrix. And the eigenvalues are like this. So like the first, the eigenvalue is the most dominant, right? So if we, and also we can get the corresponding eigenvectors, okay? So the first principal component accounts for 92.3% of total variance. So what if we just use the first 2 components, PC1 and PC2, to represent the data? Because they almost account for 100% of the total variance. So PC1 is 0.22 here, and 0.41 and 0.88 times the original features. So we can think of PC1 as kind of a general characteristics of the size. Okay, and for PC2, it has a negative components, which is here negative 0.46. So it is the negative plus, it is the length plus wingspan minus weight. Okay, so it kind of characterizes the stoutness. Okay, so there's a difference in the meaning of PC1 and PC2. Okay, so now we can explain the data with richer features instead of just using length, wingspan, and weight. But we defined our some new features as size or stoutness because these PC1 and PC2 captures can captures the total variance of data very well, and they give more informative interpretations. Okay. So speaking of the applications of PCA, we have it has a lot of applications. For example, we can use PCA to do data compression. We can reduce the remove the redundant features, and we can reduce the dimension to 2 or 3 for carrying out visualization. Okay. And we can pre-process the data sets before further feeding the data set into some other follow-up models. Okay. So lastly, we will introduce one of the most interesting application of PCA on facial recognition. So it's a famous example called eigenface. Okay. So in this example, in this facial recognition example here, we represent the face images with 100% or with 100 by 100 image pixels. So we can flatten each image to column vectors and stack them into a 10,000 by m very large data sets. Okay, and of course we need to normalize it into x tilde. And then we can compute the eigenvectors and eigenvalues of the covariance matrix, okay, which is of shape 10,000 by 10,000. And we can obtain the eigenvectors, and each eigenvector is of shape 10,000 by 1. Okay? And then we reshape the eigenvectors back to 100 by 100 2D space, and then it can be represented, it can be seen as a face image, eigenface. So this is called eigenface. And these 10,000 eigenfaces can be used to represent new faces. Okay, and in theory, we don't need to use all of those 10,000 eigenfaces, because we just need to select the top k. Okay, and top k is usually enough to be used to represent for new faces. Okay, we can project a new image vector onto a selected subset of the eigenfaces, and the projection can be used to identify whether it's a new face. Okay, so in practice, we can choose 100 to 115 eigenfaces, and the eigenfaces, if we visualize them, it looks like this. Okay, so this is the first principle, which means the first eigenvector, the first eigenface. Okay, so you cannot see a very significant patterns on this image, but this eigenface captures the majority, captures the a large part of the among the total variance in the image data. Okay, so in our assignments, we will practice something similar to the famous eigenface example. We'll use the sign language data, and we carry out something called eigen hands, because hand images essentially it's the same problem. It's the same problem of recognizing a hand versus a face. So we can represent any image of hand with a combination of the eigen hands vectors. Okay, so that's it for the principal component analysis lecture, and then I will make further announcements for the assignments for this lecture. Bye bye.